which is what I asked about, and he said that's the deadline for the final project. This is due for everyone. Then why in class 2 hours ago did you tell me that there was no such thing?
So he's gaslighting
And we
you.
still don't know what we're supposed to do for it.
I'm glad that I got my out of department done when I did.
There's a faculty member at the university present, so I'm not going to say anything.
And you're being recorded currently.
I'd say the camera is more pressing matter.
That's Jacob's. I'll just make him delete it.
Shake him down!
Yeah, no, just take a baseball bat to it. It'll be okay.
All I'm going to say,
Okay.
when it's an online class and there's been no new content for 2 months, and then you're given a test,
Wow. What kind of class online?
it's for computer science.
Who is the professor?
Adele Almagrabi.
I've not had any interactions with him.
He's a fine guy, but there's just so much confusion.
You may remind him, oh, please.
Yeah.
He
Yeah,
said he had a
okay.
cold.
Ah, okay.
That's why he
That's
hasn't.
why I always wear my mask.
Why he
We
hasn't.
avoid not ill, not sick, so that we can keep our class.
Why he's not put anything on Blackboard in 2 months. Because he had a cold.
Okay. I think we need this light, right?
Kyle's on edge.
Just over everything happening over there.
Today, our goal is try to
Just
find this position representation of operator and solve this eigenvalue problem to get the eigenstates of the optical angular momentum. So here we briefly review what we, I think last class, end of last class, right? For the angular momentum, optical angular momentum also follow the same behavior here. The definition vector, the commutator, and this eigen eigenstates and this eigenvalue problem. So today we are going to solve this in the position representation. Okay, so first, let's consider in Cartesian coordinates. And in Cartesian coordinates, the position operator R is 3 components, X, Y, Z, right? And the momentum here, we know momentum is negative H bar and this gradient operator. So gradient operator also has X, Y, Z components, now let's write down here. Partial X, X hat, I hat, partial Y, J hat, partial Z, K hat. Okay, so now we are going to first, what is the orbital angular momentum, the operator in the Cartesian coordinates by definition, right? So here, that is cross product of position operator and momentum operator. Then the position operator here, X, Y, Z, and cross products here, minus X bar, here partial X, one hat, partial Y, two hat, and partial Z, two hat. Okay, either way, you can each term to make the cross product, or I just, this my way, I prefer use the matrix to help us to make this cross product. So usually I use this. Then this first vector is X, Y, Z, right? Okay, we use this hat as the operator. And the second one, I take the minus I constant outside, partial X, partial Y, partial Z. Okay, then let's first X, the component around the I hat is this submatrix, right? So this submatrix is Y hat, right? This one, Y hat, partial Z, minus 3 hat, partial Y, I hat. That is the first one. Then second one is J. J is remove J column and this row, so that is this submatrix, right? J, partial S, partial Z, right? But we have a next side, so I'm going to here. If I use plus, so I just change the row, right? So the z per first, z here, so this and this one is z hat partial x minus x hat partial z, which is a j. And the last one is remove the k column and this row, so that is the last one is again the positive, so that is xy, x hat partial y minus y hat partial x. Okay. Then you can even know that we know that it's a vector operator, so we have x components, y components, z components. So compared with this, we immediately obtain the Lx in the position representation in the Cartesian coordinates is y partial z minus z hat partial y. And Ly is next is z partial x minus x partial z. Lz is x partial y minus y partial x. Sorry, we have minus IH bar. I have to call this constant. Okay. This is not so difficult or very straightforward, right? We just multiply. Now, next one. How about this L square? Okay. L square, you can either use this way or I start from here. So L square is, L is R cross with P, right? So that is inner product of this. Okay, so this has like kind of 4 vectors with 2 of them pair as a cross product and then together as after this the inner product. So if you remember, I just remind you, if you have 4 vector, this like vector inner product or cross product, right? Cross and inner together. So remember this be A, inner product is C, right? And there's a B, inner product is D, minus A, inner product is D, and B, inner product is C, right? We use this relation. Okay, so here I keep continue here. So this is my A, right? AC, so that is R. That's the first one, right? R, inner product is R, and then the second one, PVP. Right? Then the minus, so R to P, right? So now R, and then this P is R. The first one is easier, right? The first one is R. You can still keep vector, but R squared, right? This, and then this one is P squared. So P squared, P is here. P is here, right? So that is minus RH bar squared, and this squared. So the gradient square is Laplacian, right? So we keep the first term here, and next this one. This one is okay. I keep this. We have a minus IH bar minus. We have a minus IH bar squared. Then this part is R. We also got this gradient, and this is a gradient. Gradient is not exactly right. Here is minus h bar squared, right? And here that is, so now I'm going to put here. R, now since in the position rotation this operator is R is just itself, right? So I use lowercase r squared. And this one we know that is Laplacian, right? Right? Plus partial squared, partial y squared, plus partial z squared. So this part, we know. Right? Okay, now this one. Let me first, this is a minus plus, right? If I take minus outside, okay, let's take minus x bar outside, right? So then this is a minus. This is minus outside, this minus. Now this one is x y and z a partial x partial y and partial z. So this one is simple, right? This is just because I inner product only the same direction. So here I put here that is x partial x plus y partial partial y and then z partial z. Now this one, be careful. This one is do the grading, right? So that is first the grading is at the right hand side. Okay, so when we do that, you will see first here, partial x partial this one, how much? Partial this one, it's a partial x partial x 1, right? Okay, so because I want to rewrite the final result here, that means that. So first one is 1. And this one is 0 because y independent x, right? So same thing for z. So that means only for y to y and z to z, right? So each one we have a 1 plus 1. So that is 3. That makes sense? Okay, so now here, multiply 3, right? So now 3 I'm going to put here. So that, all right, so this is how to obtain this L square in the Cartesian coordinate. And the last one, I just gave you example how to write down the plus minus. So plus minus, we know that is Lx plus minus I Ly. And we already know Lx, Ly, right? So you can just easily to substitute this one into this. Yeah. Lx is Lx y partial z minus z partial. Okay. Now, since in the Cartesian, we can also remove the head for x, y, z. But let me write down here since I already write down. So y is z partial x max x partial z. All right. So this is the way how to present this operator in the operator in the position represented if we take with a Cartesian coordinates. Now we want to go to the spherical coordinates. The reason because we know this angular momentum associated with the rotation. So it is better to use angle instead of x, y, z, right? So now let's second, that is a spherical in sphere. Spherical coordinate. Now, similar. First, we need to write down the position operator in the spherical coordinates. It is r, because spherical coordinates are theta phi as the unit vector, right? So this is only along the r direction, right? That is position. Now, momentum. Is a gradient operator. Who remember this? I will not derive, but just give you, please remember this. since this in spherical, I think probably you know that, or you remember this. This is the r direction, and the theta direction 1 over partial theta. Okay, I need that space, so now I'll come to here. And 1 over r sine theta partial phi. Right, this is good. Okay. So now let's first, let's here, right? First obtain the, what is the spherical coordinates, how to represent the optical angular momentum operator. Again, that is by the definition, we know there's this cross product of r and p. Then r is r, right? Cross product p, we have a minus I h bar, and in this one is partial r hat plus 1 over r partial theta hat plus 1 over r sine theta partial phi. Again, here I prefer use the matrix to give me to make this a cross product. So I use the unit vector r hat theta hat of the spaces. Erase this part. Okay, I keep continue here. So I keep this minus I h bar the constant outside. Then I use this matrix r theta phi. So r is only r components, right? No theta and phi components. So that is for the vector r. And the next one is for the gradient. The r hat is partial r, this one. Then this theta is 1 over r partial theta. This one is 1 over r sine theta partial phi. Okay. I use this to help me to get this cross product. So the first one is for this r hat, right? This matrix, so that is 0. Let me keep here since right, this is for r. And then the second one for theta, so it will take this out of the column, right? So that is this one, this, but I move this one. Theta hat, and the last one is take off this factor that is r partial r 0 r. Okay, now keep here. So first one is 0, right? Because this is 0, right? So there's no term. Let me keep this minus outside. First term 0. So there is no 0 components on this r hat. Second one, this term 0, this is non-zero, right? We have a minus. Okay, you see r multiplied 1 over r sine, so r cancel, right? So that is 1 over sine theta. Partial phi theta hat. It's for this, right? And the third one is only this non-zero term. This is 0, so that is plus. Here we have also r cancelled, so that is partial theta. Or now, since this term now is 0, right? So finally, only that's 2 terms. So if we put this positive at the front, that's fine. Minus 1 minus 7, theta, partial, partial 1. This is orbital angular momentum operator in the spherical coordinates, the representation. Then we have this formula. Okay. Now next one is a little challenge, is to get L square. The L square, as we did for L square in this case, remember we have this term, kind of this partial, and in particularly the R hat, theta hat, and phi hat also change with the partial derivative, so we need to keep in mind. Now let's do that one by one. So now we are going to do L square is L, inner product is L. So we know L, right? So now here that is equal to, okay. So this is L, partial, theta, phi, minus 1 sine theta. Partial, phi, theta hat. Inner product is first the constant minus and plus, but I minus, so we have minus and plus group. Now inside is careful. First, let's do this one. I think if I do this way, that may be confused. And let me write this one in this way, otherwise, here, minus 1 and 12. Here, this one is along the phi hat, the phi hat partial theta. Put this univector in front. Theta hat, sine theta, sine. So here, I'm going to replace this one in front. Otherwise, partial theta. This one is just come to theta hat. And so this one. Okay. Then now the first one is this term. Do this and do this, right? So now let's first do this one. So now I'm going to have a sine inner product, because this inner product, right? This constant. So inner product for this one. So now I have two partial theta, partial phi hat, non-zero, and then partial theta, phi. So we have two terms, right? So that is a partial. I'm going to see partial theta, and this keeps the same. And then keep this one and do this, right? So then plus. That makes sense? So here, this term is non-zero, we keep it. So that means we have two terms to do the partial, this partial derivative to do this two terms. I first do this one, so keep this one here. And then keep this one here and do this one. So that is second, right? Okay, do the same thing for others. Then this go to here. So that okay. Now if we have a minus sign, right? So I think we keep this minus here. Also inner product here, because this one is inner product here, right? So now inside, I do these are three terms. Theta hat, sine theta, and partial phi, right? So we have, let's first do the partial theta hat, partial theta, and then keep this phi, and then keep theta hat, then partial 1 over sine theta.
How are you doing?
Partial theta, partial phi, and plus. theta hat 1 over sine theta and partial phi partial theta. So that is this one, do this two. And now we go to second term. Second term have minus theta hat over sine theta, right? Then do the partial, so now inside. First, partial phi hat, partial phi, and multiply here, partial theta, and plus phi hat keep, right? Theta keep. So this one keep, and then there's a partial square, partial theta, partial phi. Okay, that is this one. I have the inner product here. Right? This one inner product is this term. And then come to here. So then minus become plus, right? Plus theta hat over 1 over sine theta. The inside. Okay, so inside here we have also three terms, right? So we have first do the partial theta hat, partial phi, and keep 1 over sine theta, partial phi, and second one, theta hat keep the same, and partial 1 over sine theta, partial phi, right? And keep partial phi, and the third one is theta hat 1 over sine theta, we keep, then partial square, partial phi square. All right. Now we know sum of terms are 0, so now we can go to the next. But here we need, I need to remind you. This is I'm going to use here. Let's try to imagine we have several. Partial theta hat. Partial theta is minus r hat. Then there's a partial phi hat. Partial theta is 0. Partial theta hat, partial phi is phi hat cosine theta. And the partial phi hat, partial phi is minus r hat sine theta minus theta hat cosine theta. So we need to substitute those into here. Right, we have this one, this term, this term, this term, and this term. Okay. This. Partial phi hat partial theta is r hat, right? So now here, okay, I need, let's try another. I have inner product with inside is minus r hat, right? Partial theta. Okay, and then plus I have partial square, partial theta square. That is this first term. Second one, minus, hopefully that space is not minus phi hat. And then there's a partial theta hat, partial theta is a phi hat cosine theta. And since I have a sine theta here, right, and the partial phi. And keep this one. So this one sine 1 over sine theta is minus cosine theta over sine squared, right? So I have a minus cosine theta, sine squared theta, partial space. This one just keep. Okay. Plus. So that is second term. Now the third term, minus theta hat over sine theta, and inside here, partial phi partial, phi hat partial is this term, so we have minus r hat psi, right? Sine theta minus theta hat cosine theta, and this one multiply partial theta. Okay, I have two parentheses here. So this term and this term plus this term just keep it. Okay. Now the third term, and the last one is this one, right? This one plus theta hat or sine theta inside. Partial theta hat, partial phi is 0. So this term is 0, multiply 1 over sine theta, partial phi, plus, here, again, we have this 1 over, oh, that is 0, because theta is phi, right? So that is also 0, multiply phi, and the last one is theta hat sine theta, okay, now we can have almost final. You will see this lot of terms disappear. So here, this one, in the product with phi hat r hat is 0, right? Because it is perpendicular, and only this term, right? Phi hat. So that is first one is, let's keep minus alpha outside. So this one is partial square, partial theta square, right? This one also non-zero, right? Because phi, but here I didn't miss. This one I have a theta here, right? Because this is theta here. So this one also 0. Only non-zero this term. This also 0, right? So non-zero, this one is minus cosine theta. Let's see, let's turn now. Okay, minus cosine theta sine theta partial phi. Yes. Okay, so this second term is only this one non-zero. Then the third one, this inner product theta hat r hat is 0, only this term. So minus can become plus. Then we have a plus cosine theta. Something. Okay, here, this one and the sine theta partial theta. And then this one is 0. This one 0, this one 0, this is non-zero and plus. 1 over sine theta partial square. Terms, right? I have this term and this term. So this one, something on this one is coming from here, right? Yeah, the second one, partial theta partial this one. Right here I have the cosine. That's cosine. So that is theta, right? Here, this one is this term. This one disappeared because this one is this term. So This one is here, this one is here. This one, the first one is this one. This. And then this one, this term is plus. And this one is 0, 0, 0, and then 0 term. This one is 5. I have a, oh. This one's okay. This one 0. And so on. This time. So this one is second one, which is come from someone help me to find that this time something wrong. This term is shouldn't exist. There is a sine, cosine, that's a theta dot.
The derivative of
This-
phi, the derivative of sine theta with respect to phi. Shouldn't that be 0?
You mean?
On the bottom,
This,
lower, one less,
this
to the
one,
left.
to left,
The
this one.
derivative
Yeah,
of
this is a
sine
0.
theta.
Yes, yes, but did I hit this, is this one, right?
Oh,
So that is this 0, that is correct. This one is here, in this term. We have a square, and then square disappeared. So that one also fine. The only is this term, sorry. Only term is this one. So this one come from, let's see here, come from this one. Partial theta hat, partial theta is, oh, wait a moment, theta hat, theta, this I use minus r, right? This would be theta, right? So this is minus r here, minus r. Wait a moment.
in the front,
I think this is the one that I did a mistake here.
should be minus r.
Yeah, but here right now I have a minus r, so wait a moment. I have first one is partial pi. Oh, that I just made a mistake. This is 0.
Yeah.
This one is 0. And this one is minus r. So that is minus r. So then the n is 0. So I do not have this term. Yes, okay. That's fine. All right. So we have finally it's only these 3 terms. And these 3 terms now I just use this space. These 3 terms compare, you see here, this is a partial, e by partial. Let me first. It's 1 over sine theta partial theta, sine theta, partial theta. And then the last one is 1 more sine square theta, partial square, partial plus. So here, these 2 terms, you can see here, partial sine theta, partial theta. So first partial sine, this is cosine, right? Is this term. And then keep this one, so sine theta cancelled, and then partial is this term. So okay, finally is this one. So occupied time, which is student use that time. You see here, this is I gave you example how to obtain the operator, and the remaining part I will not do. I will let you know. You do yourself, to not like summarize, since that is beautiful. So now finally, L square is in this spherical coordinates is here minus h bar 1 over sine theta partial theta sine theta partial theta and plus 1 over sine square theta partial square. Okay. So we have operator, we have L and L square. Now for the Lx, if you do just do this, right? Ly use y. You have L operator, but you need to know that x, y, z in the spherical coordinates, you represent that one, and you can find this. Then the L plus minus is Lx plus minus I Ly, and I give you the final result. Lz, since we need Lz, so Lx, Ly you do yourself. Lz is, let's just give you, the z is minus I h bar, because L, remember that, z is, let's give you z is r hat cosine theta minus theta hat sine theta, right? And this is L, right? So L have a minus h bar is L is minus h bar is phi hat partial theta minus 1 over sine theta hat partial. So when you do this, you know that this is the inner product here, right? The inner product r hat with this phi hat is 0, only theta with this theta. And here, this part is on the right hand side, so you will not do the possibility for this, right? So then the minus h bar, the last one, sine, okay, this, because this one, sine cancel, right? Minus plus, so that is plus, so z. Then L plus minus here, I give you this. And I would like you to yourself to obtain this. Yes, plus minus h bar. We need this since when we solve the eigenvalue problem. We need this use the algebraic method. We need this L plus minus operator. Okay. So those are the operators which we are going to use. Now we go to solve the eigenstates. When we have the operator, so we can find the eigenstate by solving the eigenvalue problem for Hamilton the majority equation. So that is number 2, we finished, right? Number 3. I guess 3. In the spherical. Okay. All right, first, in the spherical coordinate means here, first remember this, right? If we L square apply the eigenstates give us eigenvalue and multiply eigenstate yourself. So in the spherical coordinate means we are going to multiply this spherical coordinates this basis is theta and phi, right? And r hat doesn't work, and that we don't need, right? We just need angle because you see here, only this is a theta and phi, right? And the others you can have the phi hat, theta hat. So that means the basis is this is a bra, it's a basis vector form the space, right? So that means we are going to project it. We are going to use this to define so this L square L and L. That is because, okay, this one is the eigenstates of L minus L hat in this spherical coordinate representation. I just project to this basis, right? Chapter 2. Okay, so here, this one, we already have the L square that in the spherical coordinate, so then the remaining is like let me keep here. So this is one of the things we are going to solve. You can say the equation 1. Second one, in the LZ, this also joint eigenstate of LZ, so that gave us this one, right? So if we multiply this theta phi graph, that also gives us this eigenvalue problem project into the spherical coordinates. So now our goal is to solve the equation 1, equation 2, to find this, right? So how to do that? First, we define this eigenstates project to the spherical coordinates is we use a function because it became a function y l n, which is a function theta and phi. We know this is a spherical harmonic, right? Function, right? Harmonics. So when we do this, then these two equations become L. So equation 1 is L square in the position representation. In this spherical coordinates is here, but I just later I'm going to extend this, substitute this. But here you just keep in mind now. This is already in this spherical coordinates expression. So then this one became L. YLM, theta phi, equal to h bar square L plus 1 by LM, theta, right? That is equation 1, and equation 2 is become LZ by LM, theta phi, equal to h bar and L by LM, sorry. I think we need it there. Textbook didn't use the index L. Let me use this one. Yeah. So we need to solve these two. Now let's do one by one. First, let's look at this one because this is a little simple. You see here. The LZ. Okay. I think I just do this. Let's look the LZ operator in this spherical coordinates. LZ is minus h bar partial phi, right? I just use here. Because this, so what does mean? This LZ operator only depends on this variable phi, not theta. So when you solve this one, when this LZ apply this function, that's give us the only function change here and equal to this one itself. So what does mean? This function is separable, right? Separate. I'm going to use. Only depend on theta and multiply the function which is only dependent on h bar. Since here when I do this, if you cannot separable when you do this, you have some cross term, right? If separable, then you can do this, then they can satisfy this relation. That makes sense? So that is by analyze this behavior, so we write this one. Then you can see so this became easier. We just solve separately. So now let's look at this one. And let's first we look this LZ because only for this one you will see that symbol. So first, let's look LZ. Equal to h bar ML, y L ML, theta phi is reduced to, let's look at left hand side. Left side is LZ by LML theta phi. LZ is minus I h bar partial phi, and YL is capital theta L ML only function theta, and capital phi is only function of phi, which is a quantum number only ML. Since here is only ML, right? So the only change was ML index. So here, then now let's keep continue. Since this does not depend on phi, so I can take outside, right? And only do this to that is right hand side. Right hand side is simple, we just substitute that. Right hand side is H bar ML YL ML theta phi is equal to H bar ML theta L ML theta and capital phi ML. Then you can see the both sides we can have the terms cancelled does not depend on phi, right? This term cancelled, H bar cancelled. Then now we have the only simple first order partial derivative or derivative function is minus I. Here I keep minus I here, and then only the partial by ML y equal to right hand side is just ML, right? So this one is simple. You can I think I directly on the final use, because you have to divide this to the left hand side and to multiply this to the right hand side, so this is a log, right? Log phi ML is equal to, and I multiply I both sides, so this became 1, this became I, then here. Phi. Okay, plus some constant if we do this. This is an indefinite integral. Then finally we have this function capital phi, which is exponential. Let me use this observed as a coefficient. Okay, so that is the function for z, for LZ. That part, since this spherical harmonic, this eigenvalue of L squared and LZ is two product, the product 2, so now at least the first part we can obtain. But here we want to obtain this coefficient, so we need to do the normalization, right? So to normalize this, here, the angle for phi, the value is from 0 to pi, to 2 pi, right? So from 0 to 2 pi, then there's a conjugate, mark that yourself, is equal to 1, right? That is, so when we have from 0 to 2 pi, we have a square exponential here, minus I m L5 plus I m L5 is 0, right? So that is 1 side note. Then this gives us 2 pi, right? So easily we can obtain A is 1 over square root of 2 pi. Finally, we have the normalized eigenstate for the LZ here. We have not find the M. Remember I said that L and M, ML, we need to know is this allowed integer number or the half integer number, since LZ, the angular momentum we have allowed is 2 types. So now let's see this one, how to find the value. You see here, because this one, phi is from 0 to phi, so that is rotation, right? So this function is function of this. How about this one? If I rotate this, give angle and rotate one circle, is that be equal to? This is a eigenstates, right? Or physically this state function or wave function to characterize the quantum state system. So physically, we started chapter 3, the positively. This will be single, continue, and finite. Single means if you rotate for one circle, it's be equal to itself, cannot double the values, right? So you have this value here, and after you rotate, you complete this represent one state, not two states. That is physically required for the wave function or eigenstates, right? Because wave function to describe is a quantum state of system. So the quantum state system for given angle, that's the only one system or one state. You can you cannot have the one position have a two states, right? Okay, so what that means? That means here exponent I m L phi plus 2 pi is equal to 1 over square root 2 pi exponential I m L phi, right? Then what that means? Here the only difference is this m L 2 pi is equal to 1, right? Otherwise, they cannot equal. So if equal to 1, ask ML, which value? Should be integer, right? Plus minus 0 over or 1 plus 2, all these integer numbers, right? Integers. So this is allowed or give us the allowed ML values be integer number. Then how about L? Remember the general property of this angular momentum, this M, L, only within the lowest value and the maximum value. But M, L always integer number, so L cannot be half integer, right? Or half odd integer. So L must be integer. Now we answered the beginning of the optical angular momentum. We know in general we have two quantum number. One is characterized the L square, another characterized the LZ. But now the L square, this angular momentum, the quantum number can only take the integer number. That is the answer, the quantum number for this L and ML. Okay. Now we finished the first part. This one finished. Now we are going to focus on this. So how to do this? Then we are going to use L square, this eigenvalue problem for L square. We are going to work on this. Okay. When we do this, we need two methods, or we can use two methods. One is analytical method. Another is we are going to discuss two cases. See, remember when we deal with the one-dimensional harmonic oscillator, we also work on this. So now we also do this. When we deal with the hydrogen atom, we will most cases on this one. But we just want to play and familiar with these two types of methods. So in any case, if you're familiar with one of them, when you deal with the DQ system, it can help you. So now let's go first. The first analytical method. Then we go to the first. Okay, analytical method is just to do this, solve exactly solve this eigenvalue problem or time-dimensional equation. Okay, here, so now we can look this one. And to look the left-hand side. Left-hand side of this, so L square by L m L theta pi, right? In this term. L square, I erased, but if you remember, we already derived that as minus h bar square, and then this is 1 over sine theta partial theta, sine theta partial theta, and plus sec, so partial derivative is 5, right? 1 over sine square theta partial square. Now here, y we have already separated into the two functions. Theta is only from theta, the capital theta, and capital phi is only function phi, right? Okay, this is the L square operator, and apply this. So now, let's do this one by one. I still keep minus h bar square outside. So first, 1 over sine theta partial theta, sine theta. Here, this one do this, because this is only function theta, right? So that is partial capital theta, partial theta. And the capital phi is here. Because this is not function of theta, so when you do this one, it's 0, right? So the first term only work on this theta, then plus second one is plus 1 over sine square theta, and this is only for phi. So then I take the capital theta outside. It does not work on this partial square. Okay, I still keep here. But I can take this outside, right? So take, because it does not depend to this, relate to this theta, so I can write down here. Here, and then partial theta, sine theta, partial. Second one, since we already know this phi is a function and this one is exponential, when we do the partial second order derivative, first order derivative we have a minus, we have a I m L, right? So we do the second is I m L squared. Here, this one. Then I squared is minus, so then here we have a minus m L squared over sine square theta. I missed that. Yeah, this one. Okay, that is left-hand side. Right-hand side is just here. Right-hand side is h bar square L plus 1 multiply y, right? Y L m L, so that is capital theta L m L theta multiply the capital phi m L. Then this left-hand side is both this equal, right? So the h bar square cancel. This one, and this one cancel, right? So you consider the remaining part only the function of the capital theta. Organize the finally the equation is so here this is minus inside have minus and minus become plus, right? So that is not that. And then let me get it better, then I will explain why it is d. Since only function theta, so we can use partially replace partial by d sine theta, dl and l theta is theta. Plus l plus sine squared theta dl theta 0. Here, this one, the negative sign, and this became plus. But if I multiply, then take this become positive, so this is a minus again, right? So that is minus again. And then here, if I multiply, then here the right side also negative. But if I move to the left side, it became positive. So that is positive here. Okay, this is the equation for the capital theta. Now to solve this one, if you already learned this mathematical physics, I'm not sure you have don't know this associated gender differential equation. This one, right? If you're familiar, so let's define. Then you will see define the x is cosine theta, right? Then dx is minus sine theta d theta. And let's see, also y is this function capital theta and L. This is so x is from -1 to +1 because theta from 0 to pi, right? So that is and then this sine theta, since we have sine theta squared 1 minus x squared, right? So when we use this, here this case like d theta is negative sine theta dx. Okay. So with this we just replace this equation, and you can see that is very standard, the associated linear differential equation. So here, then there's 1 over, okay, all right, 1 over sine theta here, then d theta is minus dx, 1 over sine theta, here, right? Then we have y, another y. Then inside sine theta squared root 1 minus sine theta. Okay, x dy, and again here we have. Before so still keep sine theta. Then we can cancel. D theta is minus dx sine theta. This one and this one is simple, right? So that one is plus L plus 1.
Dr. Yu,
Yes.
question about the top line. You open the parentheses in front of sine theta right here.
Yes.
Is it okay? That's what.
Sorry. Sine. Okay, here we can. Let's do this. Right. Yes. So here this. Now this is become a sine square, right? Because this, sorry, this is cancelled. This one not. This one square. So now here we have a negative d dx, and this one is sine square, right? Minus sine square, 1 minus x squared, and the dy dx. Then this part. And the L plus 1 minus n, then this 1 minus x squared. Okay, so this minus plus, and then here I do the derivative first. I keep this one to this one, so I have a second order derivative of y dx squared. And then keep this and do this one, so that is minus 2x, right? So that is 1 minus x squared. I keep this one. And second one is minus 2x dy dx. And still that part, I still keep it 0 plus 1 minus m squared minus b squared y equal to 0. Then I'm going to multiply the 1 minus x squared all sides. So you will have, oh, okay. That's enough, right? Yeah, that's clear. All right, so that is the standard. Okay, this also ratio equation, right? So that is d squared y dx squared by 2x dy dx plus lambda minus m squared 1 minus x squared y equal to 0, right? That is the standard. So the lambda in our case is L multiplied L plus 1. Only difference, right? So here, in our case, lambda is in our case is this one. Then this non-zero, non-singularity, this solution, right? So since you remember this solution is associated Legendre function P L M as a function of x is equal to 1 minus x squared to, okay, now different type of represent formula like this. So if I use textbook, it is the absolute value of m and P L x here, or P L M, if you find some other textbook, they use this one. Multiply this minus 1 to the nth power. So remove this absolute value. I'm not sure which one you're familiar, this one or this one in your class in the mathematical physics. Okay, so either one you can use, and then here we have another PL, which is Legendre polynomial. So here, so this already. Okay, let me just get the final expression of the PL, then we finish. Let's PL. Okay, I think this analytic method almost finished, but we didn't. For this theta, we have a coefficient. We need to make it, and then finally. The solution to this, but we need the coefficient to normalize. Okay, so that's be after this Thanksgiving. We have another 3 class. I think at least 1 class we can go to the chapter 6. Let me see. Have enjoy your Thanksgiving, but there's one homework. Right? Sorry. We got homework.
Multiple homeworks.
Multiple homeworks. Yeah, they also have. But yeah, well, so not fully relaxed, but enjoy the turkey.
Yes.
And for the final exam, Tai asked me some about it. So I just give idea. December 5th, right? I think that is Monday, right? December 5th is the last class. I'm going to give you this take-home exam. That is 50% take-home, 50% in class. Then in class after 1 week, that is Monday, maybe December 12th or December 13th, in class. So take-home, that is the first thing. Second is all open, even in class, open textbook, open notes, open homework. You can bring as many material you want. And the cover, is the end of chapter 3. I think that's a time-dependent part, the course duration, and chapter 4, chapter 5, and in a little bit of chapter 6, depending on how much you can cover chapter 6. Okay, that is my plan. If you have no time complete about other exam for our class, then I think we are going to take this thing.
Quick question. So, where does this come from? For the Z hat.
Okay.
Z hat should be R plus theta in the Cartesian coordinates. So where's the theta? Or am I missing something?
Yes, you need to go to the textbook, appendix E.
I haven't looked at on it, to be honest.
In the spherical coordinates.
Spherical coordinates, how to convert the Cartesian coordinates to the spherical coordinates. Yeah.
Thank you.
That's what I'm familiar
That is, yeah, that is the Z, yeah. This is the polar, yeah.
From that section.
But then you have X, R hat, Z hat, that is, yeah. Okay.
I'm assuming you started there.
I'm confused with
I started putting together my study.
I'm gonna.
Are you talking about studying for the coral?
Are you talking about the
No,
the
that's
test for math method?
that's after
For the winter, studying quals, so I can pass quals.
Dude, I guess I'm
Another
gonna have
cool.
I'm gonna have the very best break after all of this. Because, like, we had my last test December 12th. December 15th, I'm going up to the middle of nowhere, North Dakota to go test which is just hours of walking in a zigzag pattern through a field with nothing in it. No thought will be occurring whatsoever. I'm just going to be walking and walking.
Why the zigzag?
Well, because actually they're used to being hunted, and so they will sit still and then you walk past them. They will literally, like, if a pheasant's right here, some of them will, like, sit still if you walk past them. But if you fake them out and you, like, push you the zigzag, they think, he's seen me, and they'll fly.
Yeah, my roommates are planning to go shopping.
And also, you cover more ground of the field to have less places where, they can literally hide without being stepped on.
So I just have, y'all gonna be tired of me. My computer science professor has decided he is going to assign a final programming project, which then has a 5-page research paper associated with it and a 15 to 20 minute presentation. It'll be due next Friday, and he's not going to assign it until Monday.
Next Friday.
That's on that.
So we have to do the programming assignment itself, a research paper with it, and a 15 to 20 minute presentation.
In 5 days?
Yeah.
Should be legal.
So your Thanksgiving is not you need to work on this.
Well,
No, I won't. It won't be assigned until next Monday,
Oh,
and then it's
Wow.
due that Friday.
wow. So you can work on homework Thanksgiving, then you have focus on next week, focus on your
we
computation.
can always count on Dr. Yu to find the silver lining.
Don't
Yeah.
worry, we've got 2 more Spinichi homeworks in there too.
Ah,
I think I'm just gonna drop out. I made it this far.
This sounds reasonable. Let's go. Let's go, Zane.
Every day we get further along in November, the meeting is at the beginning.
Kyle.
New challenge, November. Really, I think about that a lot.